Analyzing two quantitative variables is going to start getting very interesting. In this video, we're going to look at one of the most useful methods of analysis. It is called linear least squares regression. There are three steps that we typically take to analyze a bivariate quantitative relationship. They are, in order, the construction of a scatter plot to graphically illustrate the relationship, the calculation of a correlation among the two variables to provide us a statistic to measure the strength of that relationship, and the creation of a model in which we view the values of the response variable as a function of the values of an explanatory variable. You should already know how to construct a scatter plot and calculate a correlation, so let's turn our attention to this third step. If I were to ask you to describe a single quantitative variable, such as the horsepower of automobile engines, what would you say? You might start by saying that different engines have different horsepower, thus indicating that there is variability. You might even calculate the standard deviation to quantify that variability. I suspect that you would talk about the center of the distribution and calculate the median or mean to provide more specific information about the center of the horsepower values. This would all make good sense. Now, what if we introduced a second variable, such as the size of the engine? You might still calculate the standard deviation and mean of horsepower, but I doubt that these are what you would use for your primary description. Introducing the size of the engine into the picture provides the opportunity to say something far more informative about horsepower. I suspect that you would say something like, the bigger the engine, the more horsepower it has. If I'm correct, then what you have done, perhaps without even realizing it, is to create a model that relates horsepower to engine size. The bigger the engine, the greater the horsepower. When we use linear least squares regression, all we are doing is getting a little more specific about this model. Here's the same scatter plot, though this time I have included a line to illustrate our model. We call this a regression line. This line illustrates in a picture what we've already said in words. If we increase engine displacement, essentially the size of the engine, we will increase the horsepower. We can see this relationship even if we show the model without including the individual automobiles. We can use the model to be more precise than just saying that an increase in engine size results in an increase in horsepower. This model tells me that if I increase engine displacement by 100 cubic inches, I will get an increase of somewhere between about 40 and 50 horsepower. Now our model is specific and useful, especially for the engineers who work for automobile companies. How did I know where to draw that line in the scatter plot? What we look for is a line that best fits the set of points on the scatter plot. If I wanted to draw a line to fit just one of those points, I could draw any number of lines and just make sure that they go through that point. If I wanted to draw a line that fit through 2 points, I now must draw just one line, but I can still make it fit those 2 points perfectly. But what do we do when we have more than 2 points? What do we mean by best fitting line? Here's how it works. The horsepower of every automobile deviates from the line by some amount. Notice that I'm referring to distance or deviation from the line in the vertical direction because horsepower, our response variable, is on the vertical axis. What we are trying to do is draw a line that will minimize the deviation of the points from the line in the vertical direction. What if we calculate the deviation from the line for the horsepower of every single automobile, then add these together to see how well our line fits the points? The smaller the sum of our deviations, the better fit we have with the line. This is on the right track. But there's one small problem. If a point is above the line, the deviation is positive. If a point is below the line, the deviation is negative. That means that when we add up the deviations from the regression line, the deviations above the line will be canceled out by the deviations below the line. We know how to fix this. We already saw how to address this canceling out problem when we calculated standard deviation. We simply square those deviations because we know that the square of both positive and negative numbers is positive. So that's what we do here. We find the deviation of every point, we square that deviation, and then we add those up. We find a line that makes the squared deviations as small as they can possibly be without changing the scatter plot, and that's our best fitting line. This method is called linear least squares regression. Now I can see why it is called linear because we're using a linear model. That is, we're drawing a line through the points. I also now know why we call it least squares, because we're drawing the line so that it minimizes the sum of the squares of the deviation of points from the line. But where does the term regression come from? We must rely on history to answer that question. Sir Francis Galton was an English scientist who, among other things, is one of the fathers of statistics. In 1886, he published a paper in which he showed the results of his study of the relationship of the heights of parents to the heights of their children. He found that when parents are tall, their children tend to be shorter than their parents. When the parents are short, their children tend to be taller than their parents. He referred to this as regression to mediocrity. Later, statisticians called it regression to the mean. Even though the term regression meant getting closer to the mean in Sir Galton's model, the term came to be associated with just building a model. Today, statisticians use regression to mean that they are modeling a response variable as a function of one or more explanatory variables. They say that they regress the response variable on the explanatory variable. By the way, if you're wondering why Galton's model doesn't result in everyone eventually being the same height, keep in mind that regression to the mean was just for the children of tall parents and short parents. When the height of the parents is near the mean, the height of the children tends to get further away from the mean. Thankfully, the regression phenomenon does not mean that we will eventually all be the same. Linear least squares regression models work for negative relationships just as they do for positive relationships. In this picture, we have regressed gas mileage onto displacement. The result is a model that tells us that an increase of 100 cubic inches of displacement will result in a decreased gas mileage of about 4 miles per gallon. I trust that you can sense the importance of models in statistical analysis. After all, the purpose of science is for us to understand how variables influence one another, with the possibility that this understanding can eventually lead to better control of those factors that have the potential of yielding positive outcomes in our lives.